got that. And then we have this. All right, here we go. So good morning, welcome everyone. Welcome to our course, Introduction to the Scientific Revolution. What you're looking at here are the two probably iconic pictures of the scientific revolution. On the left, you have Ptolemy's system with the Earth at the center of the solar system, or of course, the known universe at that time. And on the right, you have the very famous picture, one of the most famous pictures in the history of science, picture from Copernicus's book on the revolutions, one of his diagrams giving the sun. And this will be the great theme of our course, is going from one view of the universe to the other, and how that happened. Not only how that happened, but we can ask some questions like why it happened and what influence it has had. So hopefully we'll get a chance to explore more than just the story of scientific discovery, which is an interesting story. We have all kinds of new things that were discovered about the world in our period of the scientific revolution. But we'll see that it's more than just a story of scientific discovery, of how new things were discovered, new theories were developed. There's more to it than that, and hopefully we'll be able to get into those thoughts as well. Before we get started, just a little bit of housekeeping. Everyone, I'm going to mute everyone now, so that all the background noise will go away, so that you can make noise and you'll be muted. But what worked out in the fall, which worked out pretty well because we are a relatively small group, is that I will be stopping periodically, hopefully at least twice during the class and once at the end, for questions. And so if you can wait for those periods where I stop, that would be best for me, so I can continue on with my lecture. I promise you I will be stopping for questions, and if you could hold those questions until then, what you'll have to do is unmute yourself and go ahead and ask that question, and then I ask you to go back and mute yourself when you're finished. So I think that should work pretty well. So what I'm going to do now is mute everyone. I think I remember how to do this. Hopefully I know how to do this. Yes, okay. So, all right, so I've just muted everyone, which is a good thing. And you can unmute yourself, and you'll have to if you want to be heard for a question. Okay, so without further ado, let's start by defining some terms. Allow me to propose these definitions. They're not the best definitions. They're certainly not the only definitions of these ideas, which are very common, that we all use. But allow me to kind of set the table here for our 8 classes, because we will be talking about these things all the time, and it's important that we have we're all on the same page as to what we mean by these. So indulge me by allowing to define these words and to use them in these, what you may think of as a narrow sense. You may have a much better definition of some of these words, and that is certainly very possible. But they'll work for what we need to do over our 8 classes. So we'll start at the highest level with what natural philosophy or natural science is. So the word science, the way we use it, actually wasn't used, and the word scientist wasn't used really until the middle of the 19th century. If you were to ask Newton, for example, what he would say he was a mathematician first. But if you pressed him, he would say he was also a natural philosopher. He worked in natural philosophy. His great book, The Principia, was a work of natural philosophy. So that is an older phrase, which really for us currently would be the same current meaning as science, particularly physical science. certainly not social science in any way. The physical sciences, the major ones of physics, chemistry, astronomy, biology, all the physical sciences. And my definition, our working definitions, will be the study of things, objects, and phenomena of the physical world, with an aim to understand how the world works and why it works that way. I've emphasized these two words, how and why. We'll think about a little bit this morning, because it'll be coming up all the time as we look at these evolving theories. Are we learning about how things work, or are we also learning about why things work that way, why the universe, why the world works that way? There's a distinction between them, and we'll start making that distinction this morning. Talk about how things work, how the world works. That's a simpler question than why. You want to describe how the world works. You can start by simple observations. The sky is blue. Most metals expand when heated. These are observable facts that we all can agree upon. But there are more sophisticated observable facts. These observations are actually embodied in a scientific theory. They make no sense unless you understand some of the premises, the framework of the scientific theory. Give me a moment to define what a scientific theory is. But just to give an idea of what I mean by the more sophisticated observations, forces create a change in motion. This would be one of the great revelations of the scientific revolution, that forces don't create motion, but they create a change in motion. This is very much an observable fact, and this is actually Newton's first law of motion, or Galileo's law of inertia. Another one is that visible light passing into glass changes its wavelength. Well, again, that statement almost is not even understandable unless you understand the framework of the wave theory of light. But once you are in that theory, once you've studied that theory, then this statement, this observable fact, makes a lot of sense. What this means, in one theory, is that when visible light passes into glass, it slows down. Its speed changes, and because its speed changes, it has to change either its frequency or its wavelength. Well, the frequency is the color. When light goes into glass, it doesn't change color. Red light is still red light in the glass, so it's not the frequency that's changed, so it's the wavelength that's changed as it goes into glass. All of these statements make no sense unless you understand the wave theory of light. And that's simply my point. My point is that you have to understand the theory that it's embodied in when you talk about more sophisticated observations, although they are at base simply observations of a certain sort, because that change in speed will actually create a change in direction, and then we have the refraction of light. And that's why lenses work the way they do, by focusing light, et cetera, et cetera. Again, all of this, in the wave theory of light. So there are observations, there are things that you can describe, but they're much more sophisticated than just simply saying the sky is blue, because they're embodied in a scientific theory. And before we get to scientific theory, let me define one more term before we get to that one, which is a law of nature. And I'm going to use that phrase to mean a collection of assumptions and definitions of measurable physical quantities, and a description of the recurring relationship between them. These relationships are often expressed as a mathematical equation relating those quantities. A law describes the physical phenomena, and in some sense, the law also explains, give a reason why we see the phenomena, we experience the phenomena the way we do. And so it's in the law of nature that we first come to this idea of, are we describing, or are we explaining, or are we in some sense doing both? Well, certainly the law of nature should certainly describe what's going on. But the question is, does it explain what's going on? That business of how, describe, why, explain. So let's think about that for a moment. The how versus the why of scientific theories. Let's take an example. All known systems of astronomy have always held that the moon orbits the Earth. This has never been a debate. Okay, clearly the moon is the closest thing to us, closest heavenly body. We'll see a wonderful picture of that at some point. So it certainly completes its path around the Earth through the fixed stars and defines a month's time. All civilizations who have calendars usually start with a lunar calendar, the time it takes for the moon to go from one star, be in front of one star, to go all the way around through the stars, taking a month to come back to be in front of that star again. But we can all agree upon that. We all observe that. The question is, how does the moon move around the Earth? And why does the moon move around the Earth? Well, the how is simple philosophically. What you'd like to do is just describe the position and the speed in which the moon moves through the background stars. So here we have the Earth here in green, here's the moon going around, and we see the moon, in front of the stars of the zodiac. And as the moon moves around, we'll see it move through these stars. If we can describe on any given night where it is and what constellation it is at any given hour, what particular star in the constellation it's right in front of, in a sense, we have described how the moon moves around the Earth. Also, it would be nice to get the speed of the moon. It takes 29 days to go around the complete sky, around the starry vault. It does change speed. It has a varying speed slightly as it travels around. And it would be nice as part of that description, certainly classical physics would require that you don't have a complete description until you not only tell the position of the particle, but also its speed at any time. So that would be a very nice, complete description of the moon going around the Earth. Why does the moon go around the Earth, right? What is the explanation? What makes the moon go around the Earth? Why is it that the moon does this? And that goes towards explaining the phenomenon. Well, let me show you 3 explanations that we've had in history, among many. But here is the one that we'll be looking at in detail. This is the one that will be overturned by the scientific revolution. This is the different epicycle mechanisms of Ptolemy and also used by Copernicus. The difference, of course, is Ptolemy would have the Earth in the center and Copernicus will have the sun in the center, but they use exactly the same mechanism of a deferent circle and a epicycle circle, where the planet, in this case the moon, would be on that epicycle circle, and as it would go around, you can see in your mind's eye, as the whole epicycle circle moves around the Earth following the deferent, and the planet goes around the epicycle, you will get, this motion, rather complex motion of the planet going around the Earth. And this is the explanation that we will study in detail and get some feel for. A second explanation is the one of Kepler and Newton, where we have a much simpler situation of we have the moon going around the Earth as an ellipse. Completely different description, completely different mechanism of what's going on, but ultimately should be the same path. It should be the same description. We should get the same position and the same speed of the moon in both explanations, because it's the same phenomenon. And the third one, the modern one, would be Einstein's general theory of relativity, where again we have the moon going around the Earth, but we are moving in the fabric, the 4-dimensional fabric of space-time. The difference between these explanations, well, one is pure geometry. Okay, it's actually, if you think about it, all these motions here on circles, these are all motions at constant speed. The epicycle is going around the deferent at a constant speed, and the planet is going around the epicycle at a constant speed. And if you know the sizes of these circles and the speeds in which they're going around, it's rather straightforward geometry to calculate exactly where the planet would be, in this case, the moon, at any time. In a duration of time, you would know how far it has gone around the deferent circle, how far the planet has gone around the epicycle, and you can pretty easily, using geometry, pinpoint exactly where the planet would be with respect to the Earth. So this is a mathematical model, but it's a model based upon pure geometry. The second model is, of course, the law of gravitation. Got to throw in Newton's 3 laws of motion to boot, but at base we have the law of gravitation, and again another model. This is also a mathematical model. It's not primarily a geometric model. This is primarily an algebraic model. These are equations which are governing the aspects of the path of the moon, the position and the speed. Of course, those equations will turn into geometric positions and speed, but it's a primarily different kind of explanation, a more sophisticated one, where it's not just pure geometry, but you can calculate things using these equations involving the measurable quantities that we're interested in, like distance, like position, like speed. And the third explanation, Einstein's of general relativity, well, we go back to pure geometry. We go back and close the circle, and here we have a more sophisticated geometry for sure. This is now the Riemannian geometry, a 4-dimensional manifold, quite a mouthful, but it is at base geometry. The reason why the moon goes around the sun is because of the geometry of the universe. That the Earth, the gravitational field of the Earth, creates a curvature in space-time, and all the moon is doing, it's very simply moving along the simplest straight line in that space. And that simple straight line turns out to be equivalent to all the other paths of the other explanations. It goes around the Earth, passing those stars of the zodiac at the varying speeds because of, as it moves in a straight line in this very complex Riemannian geometry of the 4-dimensional space-time. So an idea of different explanations of the same description. And of course, they're all embodied in theories, the importance of theory. One more set of terms, allow me, before we get started. Finally, yes, what is a scientific theory? That is not, scientific theory does not fit the phrase, oh, well, that's just a theory. No, no, no. If that's just a theory is what you mean in colloquial English, that is not what a scientific theory is. A scientific theory is much more than that. A scientific theory is a collection of assumptions, definitions, and laws of nature, which you've just defined, which describe, explain, predict some range of physical phenomena. It definitely does describe, explain, and predicts. It is not just a theory in that colloquial sense. So let us take that as our definition of scientific theory. And finally, well, not finally, but very importantly, going up one higher level, we have the definition, I'll use the word paradigm, coming from Thomas Kuhn's famous book, The Structure of Scientific Revolution, used the word this way. Paradigm is a set of concepts, thought patterns, including assumptions, definitions, scientific theories now, research methods, standards of investigation and proof. Yes, it's a very encompassing, comprehensive way in which we understand the entire physical world and how it works. That would be a paradigm, and we need to go ahead and study that in our course. A paradigm is another way of saying it's a model of reality, a view of reality, a theoretical framework for thinking about how the world works the way it does. Paradigm is famously said by a philosopher of science that a stable paradigm should be clear, comprehensive, and awesome. That is, it is awesome in its comprehensiveness of how much it explains, how many theories fit into the same paradigm, how so much of these explanations that we think of, our mental furniture, is comfortably interconnected by one set of ideas. A stable paradigm that is one that's going to last should be clear, comprehensive, and awesome without being stupefying. It shouldn't be so stupefying that we can't even comprehend it, that we can't internalize it. And that could be one of the problems with our one of our most current paradigms, that is of the quantum theory. The quantum theory is, in fact, still to many of us, even to scientists, stupefying. The famous phrase of I forgot his name, I'm having a senior moment, saying that if anybody, that no one, I can safely say that no one understands quantum theory. Niels Bohr also said the same thing. So it is something which is all those things, but maybe it's more than awesome. It is stupefying in that sense, and so maybe it is not stable. And finally, the subject of our course, our final definition here: what is a revolution in natural science? We want to study an example of such, and we'll define a revolution in natural science as the occurrence, or maybe better, the process of the then current paradigm being replaced by another in the minds of most scientists working in the field. Yeah, it's not going to be a revolution when you and I change our paradigm. We're going to be way behind the scientists who work in that field. But when the majority of them begin to come around, stop thinking in the old paradigm and start thinking in the new paradigm, then I think it's safe to say we have experienced a revolution in natural science. And that takes a while. And it's going to take even longer for us laymen to catch up to this thing. Right now, again, going back to the quantum paradigm, I think it's safe to say that we do not have that paradigm in our heads. I don't think any of us are working particle physicists or cosmologists. So we have the classical paradigm, the one that we're going to be going to by the scientific revolution. That's the one that we're comfortable in. But there are some scientists working in the field which are becoming comfortable in this new paradigm, this world of undeterministic behavior, of probabilistic behavior, of the Schrodinger equation being the only thing that we can definitely say about reality, and on and on. Some scientists are, in fact, incorporating that, internalizing that, and just working with that as a new view of reality. We are not pretty much up to that. It is still quite stupefying to us. Things like entanglement and ideas like that. Very difficult for us to be comfortable with. Okay, why is a theory replaced by another theory? Because that is basically our story. Okay, one theory, more importantly, one paradigm is going to be replaced by another paradigm here. That is the scientific revolution. And underneath that, theories will have to be replaced. When you start replacing theories, you are now on the road to replacing the whole paradigm. Well, one reason is that it explains phenomena that the old theory doesn't. Duh. Yeah, that'll do it if a new theory does a better job, if it explains things that the other one can't. Some examples: Copernicus was able to calculate the relative distances of the planets. If you call the distance from the Earth to the Sun 1, he was actually able to calculate using his new theory, his model, that Mars was 1.5 distance from the Sun, that Jupiter was 5 units of the Earth from the Sun, etc. Ptolemy's system could never do that. Newton's law of gravity was able to explain the periodic motions of the tides. And general relativity can explain the famous precession of the perihelion of Mercury, the first actual thing that he was able to verify privately in his theory. If you're not familiar with this one, here is the motion of Mercury going around the sun. The perihelion is simply the closest point of Mercury in its orbit. And if you think of the orbit as a wire, it turns out that what has been observed since powerful telescopes of the 19th century, that this whole orbit, the whole wire, is turning very slowly around the sun. So if the whole wire is turning, then certainly the perihelion is turning. The whole thing is turning around. The whole wire is going around while Mercury is going around and around in its orbit. So this is called the advance of the perihelion of Mercury. And Newton's theory could not account for this. He could account for a part of the motion, but not the motion that was truly observed. And Einstein was able to one of the first deductions he was able to make from his general relativity before it was even published in his study. He was able to do a calculation with his new equations to, in fact, get the advancement of the perihelion of Mercury correct. He says in his writings that he was so excited when he was able to do this, that he was not able to sleep for 2 days. He just walked the streets of Berlin, unable to sleep, going over in his mind how he was able to actually produce this prediction from his equations. Another reason why is that a new theory will replace an old theory with a very important, crucial, distinguishing experiment. There have been some very famous experiments in the history of science which are considered absolutely crucial, and when this new theory can produce that correct result where the old theory could not, this is a very dramatic example of the new theory coming into its own and starting to be taken seriously. An example of that would be the heliocentric theory of Copernicus being able to predict the observed phases of Venus, just like the phases of the moon, going through a quarter moon, a half moon, a full moon. Venus does the same thing. This was not seen until the telescope of Galileo, but once it was predicted, but not seen until the telescope. And when Galileo turned his telescope on Venus and saw the phases of the moon, this was a very, very dramatic discovery, and really shook the whole notion of the geocentric system. The geocentric system could not explain this. We'll see why. In the geocentric system, Venus is always in front of the sun. It's always traveling between us and the sun. So it's always, in a sense, backlit. Whereas in the heliocentric system, Venus is going all the way around the sun for us. And it is sometimes backlit and it is sometimes full lit. And so we would get the full phases, we would get the half Venus, we would get the full Venus, just like the moon. And this is what Galileo saw with the telescope, something that could not be, what was not predicted, was not explainable by the geocentric system. And the last example I have for you is the very famous one. I hope that most of you are familiar with the great observation of Arthur Eddington in 1919 of showing that in solar eclipse, that the stars near the sun were actually askew. They were actually slightly displaced from where they usually are in the sky because the light being bent by the strong gravitational field of the sun. Okay, one of the most important predictions of general relativity, that gravitational fields warp space and time, and therefore would change the trajectory of a light wave going near it. This was verified again by very elaborate going out to Africa with all of his equipment and taking photographs during the eclipse. So they knew what they were looking for, just as Einstein knew what he was looking for to predict the perihelion of Mercury. They knew what they were looking for, and they found it. And this is the event that made Einstein a world, the most famous scientist in the world, when this was confirmed. One more reason why one theory will replace the other, just simply when it makes predictions out of the blue that no one was expecting, that the old theory does not. Some examples is that Copernicus' theory predicts that the fixed stars are very, very, very far away from the Earth. That must be the case if Copernicus' theory is true. And so he predicts it. He said, well, then it must be true if my theory is true. This was something that was not expected at all. And of course, not considered true. There was this prediction that was considered one of the great weaknesses of Copernicus' theory, because it doesn't seem like the stars are all that much further away than the furthest planet being Saturn. Newton's law of gravity was able to explain the bulging of the Earth at the equator, something that again was not expected, that the Earth is not a sphere, but more like kind of like a squashed orange. Newton's gravitational theory predicts this, and once it was verified, it was a very dramatic support of Newton's theory. And finally, Einstein's general relativity originally predicted the expanding universe. I say originally because of the famous story that it was thought by Einstein and everyone else from the beginning, from our period, from the time of the Greeks, that the universe was more or less constant, more or less fixed, more or less always was the way it always has been. This was something that led right up through to the beginning of the 20th century. And when Einstein develops his theory, it was much more natural, looking at his equations and his basic concepts, to have a term in there which would allow the universe to actually expand over time. But he rejected this. This couldn't be so because it was always thought that the universe was more or less fixed and constant. So he took out that term, and he famously called that the greatest blunder of his professional life, because it was not long after, 10 years after, where Hubble did verify that we do live in an expanding universe by noticing all of the galaxies moving away from us. And that term, which now is called dark energy, or the cosmological constant, is put back into general relativity. So if Einstein had trusted his math at first, he would have predicted 10 years before the verification that in fact the universe was expanding, but he did not. And so he called it the greatest blunder of his scientific career by not holding to the math that he first derived. So here are some simple reasons, not very profound, of why it is that we have changes from one theory to another. Is a theory true or false? A good question. Is a theory true or false? Well, certainly we can prove theories to be false, right? We just have to find things that the theory predicts which are not true. That would be pretty convincing. Aristotle's theory of motion holds that all bodies fall at speeds proportional to their weight. We can easily verify that that is not true. And of course, Galileo did that by dropping the two different weights of balls from the Tower of Pisa, right, to show that they fall essentially at the same time. The geocentric theory predicts the incorrect phases of Venus, as we've mentioned, and Dalton's early atomic theory held that atoms cannot be broken. They can't be broken into smaller pieces. They are the smallest possible piece of matter, and that all atoms of the same element have the same weight. Well, neither of those two statements turn out to be true. In fact, we learned in high school chemistry that atoms are made up of electrons and protons and neutrons. And in fact, different elements, so the same element, do come in different sizes. They come in different weights. They call the isotopes. Hydrogen, for example, comes in 3, has just a proton in its nucleus. Deuterium will have 1 neutron along with it, and tritium will have 2 neutrons along with it. 3 different weights, but all being the same element of hydrogen. So both these major tenets of Dalton's theory turn out to be false, and therefore Dalton's theory has to be at the very least, modified. It is not true. Can a theory be proven true? That's a very interesting question, and that's something that we will hit upon, right? We'll rub against this. Was Copernicus's theory proven true eventually? Well, philosophically, what does that mean? We realize that a working theory describes and explains phenomena, but really what is a theory? It's really at base an abstraction of reality. It's a theory is always in danger of being falsified, right, by some unknown aspect of reality cropping up, out of nowhere, like all of a sudden, discovering the bulge of the Earth, something that was not suspected. So an experiment or something coming just out of phenomena can always shake the foundations of a theory by showing something to be true, predicting something to be true, which the theory cannot account for. Examples: Newton's law of motion can't account for the apparent increase in mass and the interdependency between distance and time, all observed when speeds of particles get close to the speed of light, right? Newton's laws cannot account for that. That requires special relativity. Newton's law of gravity can't account for the bending of light, as we saw with Eddington's verification in 1919, but general relativity can. Quantum theory can account, the wave theory of light can account for light coming in discrete quantum packets of photon energy. We need to move to the quantum theory developed by Planck and Einstein to begin to understand that. And finally, maybe the most dramatic one, our most current theories, our greatest theories of quantum physics and relativity cannot explain what we see as what we now call dark matter, which, according to the cosmologists, will tell us makes up 80% of the matter of the universe. is in dark matter and we can't explain it. So, yeah, is our great quantum theory and relativity theory in danger of being falsified? Well, at the very least, it's going to have to be modified. At the very, very least, if we're going to accommodate this dark matter. That's even before we get to dark energy. Okay. Last slide before I'll ask for questions. You look at the idea of a theory compared to truth. I kind of broke it up into this matrix, which may be helpful. If you look at the two columns, we have a column of current theories and non-current working theories. Well, a current theory is the current theory, our best explanation right now of that phenomenon. A non-current working theory, what I mean by that, it's a working theory. It's still used. It's very, very useful, but it's not current. It's been replaced by something else. On the row side, we have theories. Some theories have a very extensive domain of explanation. They explain a tremendous amount of diverse phenomena. And some theories have much more of a restrictive domain, and they come in both current theories and non-current theories, as we'll see. The best of all possible worlds would be that first top box, that they are current and they're very, very extensive. Quantum theory, the laws of thermodynamics are a good example of still current theories, which have a tremendously wide range of explanation of various different kinds of phenomena. Okay. Current theories which are more restrictive would be something like general relativity and the photon theory of light. Very famously, general relativity only explains gravity. We still cannot incorporate the ideas of general relativity into the quantum theory of the small, that there's a fundamental incompatibility between the two, so its domain is restricted to just the very, very large, and the phenomenon dominated by the gravity. On non-current working theories, Newton's laws of motion and Newton's universal gravitation, they're no longer the best explanations for those phenomena. But NASA and the European Space Union does very well using these two theories, flying all their space missions around the solar system. This is very much a working theory, these two theories, but they're not our best explanation anymore, theoretically. Newton's laws of motion have really been, overshadowed by the mechanics. The classical mechanics of Newton's been overshadowed by quantum mechanics, and of course, universal gravitation law, as we understand it, is now overshadowed, replaced by general relativity. And finally, that last box down the bottom, the poor cousins, the ones which are no longer current, and they even have a restrictive domain, but they're still a working theory. Examples of those would be the fluid theory of heat and the fluid theory of electric charge, two old theories basically of the 1800s, even as early as the late 1700s. But still, heat has many properties that act like a fluid. And electric charge also has many mathematical properties that act like a fluid. And they still are used in some simple explanations. Some easiest ways to understand the motion of heat, the properties of heat and electric charge, is to think of them as a fluid. So it is non-current, certainly. This is not the way heat and electric charge are explained anymore. This is not an acceptable explanation, but it is a working theory. I think that this column here, this last column, is a good example of describing but no longer explaining. These things do describe nature very, very well. They're working theories. They're used today, but they're not the current explanations. We have different explanations. What does that mean? We have different theories to explain, because the explanation is in the theory, not just the simple descriptions. Okay, let me take a break here and ask for questions of what we've talked about so far. Please unmute yourself and fire away. Any questions?
I have a question about the moon. Does the moon rotate itself? I mean, we only see one side of it.
Very good. Excellent observation. Wonderful. You are absolutely correct. The moon does rotate just the way so that it'll always have the same face towards us. Not a coincidence. It turns out that you can prove that the law of gravity does get to make the moon be in sync, that its spinning is in sync with its revolution around the Earth. But that is a true phenomenon. Yes.
Thank you.
I have a question about maybe you could explain better the difference between a theory and a law. Seems to me they both sort of define the same thing.
No, they don't. If you go back to my working definitions, and I asked you to just accept my definitions, please ask a question about them. But a theory encompasses laws. Okay, a theory is much more than a law. Let's see if we can go back to the distinction, because it is an important distinction that you're making. Yeah, a law of nature is something a bit more narrower. It's a collection of assumptions and definitions of measurable physical quantities which describe and explain. That's a law. For example, the law of gravity, the laws of electromagnetism, the laws of the focusing of lenses in glass with light. A scientific theory is a collection of assumptions, definitions, and laws of nature which describe and explain a whole range of physical phenomena. A scientific theory is much broader than just any individual law that's inside of it. And I think if you give me a chance as we go through looking at the various laws and theories and paradigms, both of the ancient world and of the scientific revolution, I think my distinction will become clearer. Any other question?
Yes. Let's see how to put this. When in the space program, it's Newton's. It's my understanding that it's Newton's laws that enable us to fire the rockets and predict and know exactly how far where they're going to go and how they'll be affected by the orbits of various planets and things like that. Can Einstein's theory, which is more current, as you said, can the math of Einstein's theory do the same thing in terms of practical application that Newton's laws do?
Theoretically, yes. Practically, no. Einstein's equations are so complex that the math would be hopelessly complicated and unworkable to work down at the level of true trajectories of space missions landing on Mars or landing on comets which are going around Jupiter, which was recently done. No, you would never try to use the equations of general relativity to do those kinds of calculations, because the math would just be hopelessly too complex. But theoretically, if you could solve those equations, that is in simple cases, in very, very simple cases of just looking at the simple orbit of a planet going around the sun, Einstein's equations do predict exactly the same simple orbit that Newton's equations do. But the complex stuff that's going around firing rockets at different times to change the trajectories of the space mission as it goes into its flight paths, no, you would never be able to use Einstein's equations, although theoretically you could if you had some kind of super powers of mathematics.
So Newton still in a very real sense, Newton still reigns in terms of his theories and his laws of motion.
Absolutely. It reigns in terms of NASA and the European Space Center and the people who fire off rockets in China. Yes, they all follow Newton's laws. They have no need or interest. Those engineers have no need for general relativity. Okay, let me go on. I'll stop again. So that's a kind of a general idea of of some ideas about theories and that such. Let's go ahead now and take a look at one of the paradigms, the old paradigm of the ancient world. Let's go through some of those ideas. Here are the teachings that Copernicus would have been taught at university when he went in his 20s. This was the prevailing best science of the day. The universe is finite, both in time and in space. Its size and fundamental structure is unchanging. Einstein agreed with that. Okay, 500 years later. And basically, it is this two-sphere universe, as it's been called. We have the Earth in the center and the celestial fixed stars around it. The fundamental structure of the universe. The Earth is a sphere at rest in the center of the universe. The universe is a spherical shape itself, and its outer boundaries is the sphere of the fixed stars, which revolve around the Earth once a day. The entire sphere, the entire universe of that sphere revolves around the Earth every day. Here's a very famous work of a man by the name of John Hollywood, published, written first of all in 1230. It was one of the first books published, 1472 at Gutenberg's printing press was in the 1460s. This thing went through 84 editions of printing, and it was used right up to the time of Newton. It is basically a watered down version of Ptolemy, Almagest, and it was the most popular, important work explaining astronomy in the Middle Ages. So this paradigm lasts a long time because of books like this being taught again and again through many, many generations. Interesting, this page I pulled out shows the three explanations that Aristotle gives of why the Earth is round. These explanations come from the Pythagoreans. He gives Pythagoras full credit for this. And this, if anybody still has the idea that people thought the Earth was flat, hopefully this will dispute you of it. You know, all educated people in the Middle Ages, all the way back through to the ancient Greeks, knew that the Earth was round. Everyone always knew the Earth was round. If you were a farmer who never traveled more than 20 miles away from where you were born, maybe you thought the Earth was flat. Okay, that's certainly a reasonable such, but anyone educated certainly knew that the Earth was round. And these are the three examples. The one down the bottom is probably the easiest, right? Looking at this, the horizon, the ship sails away, it seems to sink into the ocean because of the curvature of the Earth. The other two, here's another relatively simple one. This is the lunar eclipse, where the Earth gets in the way of the sun and casts a shadow on the moon. And that shadow is a curved shadow. So the Earth must be a curved object if it's creating a curved shadow on the moon. And the third one is probably the most sophisticated, is that as you go north and south on the Earth, on the spherical Earth, you'll see different constellations. Constellations will be in different heights in the sky, again, because of the curvature of the Earth. If you've ever vacationed down in the Caribbean and you look at want to find the North Star, I always kind of like to find the North Star wherever I go. And I remember the first time I went down there, I'm looking at the North Star, you know, I'm looking up around 40 degrees, which is where it is, we are back home. I'm looking up and I can't find the North Star. Where the heck is the North Star? It's always supposed to be out all the time. That's what we're told. Where the heck is the North Star? Until finally I realized it was just above palm trees. It was quite low. It was, you know, not at 40 degrees, but more like 20 degrees where my latitude was. So yes, the reason why the constellations, the whole sky moves and it looks differently as you go north and south, again, is because of the curvature of the Earth. And these explanations were presented by Aristotle to show that the Earth was round, and he again gives full credit to the Pythagoreans for giving these explanations. More teachings. The behavior of nature in the terrestrial world, that is the world below the moon, is completely different from the behavior of the heavens above the moon. Completely different spheres of phenomenon. The study of physics, that is of the terrestrial world, composed of the fundamental elements of earth, air, fire, and water, is completely different discipline investigating those natural processes compared to the study of the heavens, astronomy, which is a part of mathematics. Completely different spheres of reality. The universe, from the path of the moon and above, including all the heavenly bodies, are made up of, not only are they different, they're made up of a totally different element. They're not made up of earth, air, fire, and water. They're made up of an element called the ether, which is distinct from earth, air, fire, and water, has its own behavior, its own properties. And the ether is something which is perfect, it's unchanging, and can only move in the perfect way. And what is the perfect way of motion? Well, clearly the perfect way of motion is moving in circles, moving in constant eternal circles at constant speeds, okay? That is the only possible way in which something as divine as the heavenly bodies should move. And that's the way the explanation has to be, to find a way to show that the motions of the heavenly bodies follow the behavior that is fitting of that kind of substance, which is in circles, moving at constant speeds. And here, of course, is the famous picture. Not Dante did not draw this picture, but the famous picture of Dante, the Divine Comedy, of the circles of heaven and the circles of hell. Okay, we have 9 circles of hell. Yeah, famously, as he goes through, going down to the various circles. And for symmetry, we have the 9 circles of heaven. There's the circle of fire, which is the highest circle above the earth, and then we have the moon and Mercury. So we have fire. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 to the fixed stars. So the 9 circles of the heavens balancing the 9 circles of hell down in the bowels of the earth. The top circle here is the prime mobilium, right? The prime mover that makes everything else move. The classic medieval view of cosmology. Let's take a look. We'll look much more closely to, next week at the motions of the sky, so that we can understand these motions. We can understand where we're going from Ptolemy's model to Copernicus's model. But just to get us started, here is our 2-sphere universe, fundamental universe of the medieval paradigm. And we have a 3rd sphere here, the sun. You're surprised that I'm showing you a modern model when we're talking about Copernicus's model. This is a very useful model. This is very much a working theory. Okay, when you take a course in positional astronomy, this is the model that we use. Okay, the geocentric model is a very useful working theory to understand, to get our heads around the motion of the stars and the planets as it moves in the sky. We think of it as where we would see it if we sit in our lawn chair at night and watch. This is what we will see. Okay, this is an embodiment of that model. So again, a very nice distinction between describing and explaining. Does this explain? Well, people will say, no, this is not the right explanation, but it sure is a good model. And so in that sense, it can, help us internalize what that description is. And so what the model says is that the whole sky, the celestial sphere, turns around the earth once a day in that direction, because we know the stars, here's our good old North America. The stars rise in the east and they set in the west. So the sphere is moving around this way. However, we know that the sun has a path through the sky. It takes a year to go all the way around the ecliptic, the path of the sun, and it moves in the opposite direction. As the stars move from east to west, as they rise in the east and set in the west, as you watch the sun slowly move day by day through the constellations of the zodiac, because that's what the constellations of the zodiac are, the constellations that we see behind the ecliptic. That's why they're so important. They are the ones that frame the path of the sun. The sun actually moves from west to east. You may say, how do we see the stars behind the sun when the sun is out? You don't see the stars. Very true. But if you're very careful and you're a sky watcher and you've been watching the sky for 2,000 or 4,000 years, you get ways of studying where the sky is with respect to the sun. For example, as the sun sets, we see what constellation is behind the sun, just as the twilight begins to reveal what the sun is. And we'll find 2 months later that no longer is Gemini behind the sun, but now Leo is behind the sun. And if you do this for centuries and centuries, as careful as you can, you do get to finally map out quite accurately the path that the sun moves through the sky. And we'll look at this more carefully next week. Here's a nice picture of the moon moving through the sky. The moon moves about 12 degrees every day, night to night. And so there it is moving. This doesn't take a year to go around. This is much faster. This goes around in a month. This is our definition of the month. 12 degrees every day. 12 degrees times 30 days is 360 degrees. You go all the way around, and such the month. Notice not only is the moon moving, but Mars is also moving. Not as much, of course, not as fast, but Mars certainly is moving every night, slowly. Okay? As it goes around the Earth. Jupiter and Saturn are also moving, but they're moving so slowly that we can't see them from night to night. Okay? You would need a telescope to notice the motion of Jupiter or Saturn. You might not even be able to notice the motion of Saturn. Saturn takes 30 years to go around the sun. Motion is very, very slow. Jupiter takes 11 years. But Mars takes just 1.5 years. And so that is quite a fast motion. This, by the way, is a live link to a planetarium program, which I invite you to play with, the sky. It's quite self-explanatory. It's a lot of fun. I encourage you to play with it. A little bit now about, we've talked about the sky a bit. Let's get down to Earth and look at the elements. There was a fundamental chemistry going on in the Middle Ages, going back again to the Greeks. The fundamental substances of the Earth was earth, air, fire, and water. And they had a mathematical equivalent of the so-called Platonic solids, the regular solids. Here we have the clunky cube is what was identified with Earth. And the sharpest, the tetrahedron, the 4-bodied system with fire. The most round, the hexahedron with water. And the octahedron with air. And this comes from Plato. Plato being a very much Pythagorean, very much holding to the subscription that the universe is a mathematical universe governed by mathematical laws. Plato was very much a disciple of the Pythagoreans. He's the most famous and the most influential Pythagorean in history. And this idea, this association comes from the teaching of Plato. And finally, the last, the dodecahedron, symbolizes the ether, that fifth element, which is unlike all the other ones. You see that all the other ones are either, their faces are either squares or equilateral triangles, whereas very differently, the dodecahedron, the common regular face is a pentagon. And so it is distinct, it is different than the others, and befittingly is the distinct ether, the divine element made up, making up the heavens. We move on to Aristotle, his teacher, his student, Plato's student, a lot less mythical, a lot less mathematical, more grounded in observation. And he kind of took air, earth, fire, and water. Well, there's something even more fundamental than that. There are these categories, these polarities of warm and cool and moist and dry, and they give rise to all kinds of phenomena, including the substances. And so more of a chemistry being mixed here. Aristotle was the great creator of categories, as we'll see as we look more and more into his theory of motion. We'll see the wonderful categories that he creates and the kinds of descriptions and deductions he can make from his categories. He's not the father of logic for nothing. And just taking it a step one further to see the influence of Aristotle and his categories, we have the famous humor theories of medicine of the ancient world, very much going right up through the late Middle Ages and the Renaissance, coming from the great physician of the ancient world, Galen, of the different humors, different biles, black bile and yellow bile and phlegm and all that kind of stuff. And the idea that sickness was you're sick when these humors are no longer in balance, when there's too much of one and not enough of another, and that's when you get sick. And the way you get healthy is to go back and bring back that balance, right? And so therefore, we have the obvious therapy of bloodletting. If there's too much of something in your blood, well, let's take some of your blood out of you, and that will restore your health. And so we have the therapy of bloodletting, which lasts way beyond the scientific revolution. We don't get the revolution in medicine until much further. So again, this notion of categories of dividing up our mental furniture into these simple categories that allow us to understand reality as we see it. Okay, let me stop again before we have our last set of slides. Any questions so far on what we've talked about in terms of I'm developing a paradigm of what Copernicus would have been taught as a university student of how the world works, what the universe is like. Any questions so far? Okay, our last set of slides. So let us, I'll give a name to the paradigm of the ancient world that moved on through up to the Renaissance before the overturn of this paradigm by the scientific revolution. We'll call it the classical civilization / Christian paradigm. Yeah, it's a mouthful. Maybe we'll call it the CCC paradigm. But of course, it has elements certainly of the classical civilization of the ancient Greeks, and very much has the Christian theology of the church as part of the paradigm. So it is a merger of the two. So it is an appropriate title, as clunky and long-winded as it might be. Most explanations of the phenomenon inside this paradigm are teleological, which means that the explanations are go to the purpose of why these things are so, as opposed to the causal principles or the laws of nature, which make them so, which make them arise the way they are. That wasn't the fundamental explanation or the description. You would describe something by saying what its purpose was. That was the explanation that was most important in this paradigm. And we'll see an example of that soon. Easier to explain it with an example than with a philosophical discussion. But a few other points about some of the elements. The timeline of the world was finite to the people of the late Middle Ages and the Renaissance, centered at the life, specifically the incarnation of Jesus. It began about 5,000 years before the life of Jesus. The current date, whatever it would be, 1550, would be the number of years since the birth of Jesus. And when will the world end? Well, no one really knew, but probably somewhere around 5,000 years after the birth of Jesus. Kind of a nice symmetry. No one really knew when the second coming was coming, but it was coming. It was coming not so far away, clearly not any further away than when the beginning was. So the world was very finite and comprehensible in time. It was also finite in space, right? That the two-sphere universe of the Earth in the center and the global stars around it, the fundamental structure of Aristotle and Ptolemy. The universe was something you could get your hands around, that certainly God could get his hands around, that anything beyond that was heaven. Until the voyages of discovery, right, in the 1500s, Columbus and Magellan and all those folks, the center of the world was Jerusalem on all the maps. And Jerusalem, approximately, there was Ireland on one side and China on the other, and Jerusalem in the middle. And that was basically what the world was like. It was one continuous landmass. And there was some kind of a small ocean between the two, but you wouldn't want to cross it. Didn't know quite how big it was. But it was just one mass, and that was the Earth. That was the globe. The elements earth, air, fire, and water, and ether are different entities. They're different entities. Those four, each one is a different entity having different properties, earth, air, fire, and water are all different. They create a kind of a chemistry because we are all combinations, complex combinations of those four. And then the fifth being the ether. The heavens are divine and unchanging. The ether is a divine, unchanging substance, eternal, while the earth is base and always in flux. Very fundamental idea that common sense that everyone knew, part of the fundamental paradigm that has to be overturned if we're going to move into the modern world. And the last one I give is an example of a teleological explanation. The universe was created. Why was the universe created? It was created to provide a proper stage where each person be able to earn their right to go to heaven. That was a perfectly satisfactory, it was more than a satisfactory, that was a very, now I understand. I understand why I'm here. I understand why all this is here. Why is the moon here? Why are these planets here? Why is all of this here? Well, here's the reason why. That's a good reason. It's a very good reason. It gives me a chance to live and spend the rest of my eternity in paradise. This is a very good reason. And this is not to mock that reason, okay? I would never want to do that. Okay? But it is so different to explain this, give this kind of reason compared to the Big Bang. Why are we here? Well, we'll go through the crazy story of the Big Bang. Okay? That is the contemporary reason now in science. The contrast couldn't be more different. Some developments which directly contributed to this paradigm as we understand it, important milestones in history, I think that we'll all agree. The introduction of the Hebrew Arabic numerals, 1 through 9, decimal place value, moving away from the Roman numerals, quantification coming into our culture, engineering of the Gothic cathedrals, mechanical clocks, marine charts, the rise of banking, the institution of formal bookkeeping. All of this are new ideas that come into the late Middle Ages and the Renaissance, which contribute to this latest paradigm that we have before the scientific revolution. The Latin translations from the Arabic into Latin of the great classical works and the Islamic works coming basically from Constantinople and the Eastern Empire. Most importantly, the works of Plato, Aristotle, Euclid, Apollonius, Archimedes, and Ptolemy. Hopefully we are all familiar with all those names. The rise of towns and cities, right? Populated by engineers, artisans, and merchants, not just farmers, not just soldiers, nobles, and farmers. Okay, there's more to life than just nobles, soldiers, and farmers. There are this class of people, which gives a whole different rise to the intellectual life of society. And finally, the rise of universities, a very direct, clearly, contribution to the intellectual life, teaching philosophy, theology, law, and medicine, the great subjects of the university. Really the only major subjects taught at the university. Just an example of the paradigm being developed. Here is Ptolemy's most famous map, going back to Ptolemy's time of 150 AD, the map of Europe, very impressive for 150 AD. This finally made its way into Europe in 1400 from Constantinople. It finally arrived in Florence. You can imagine the impact that this map had on the people of Europe in the 1400s, when they saw this. They knew nothing like this, the scope of this map. Just took their breath away. And not long after, 88 years later, in that quantification, the cardiologists began to learn how to make maps again, the mathematics being developed again using the new number systems. Yeah, pretty impressive map for 1488, right? This is before the voyage of Columbus. This is before the voyage of Magellan. Okay, not bad. Okay? Not a bad start. Impressive development of the world. And this is this idea, of the center. And finally, the two dominant scientific theories that are the bedrock of this paradigm, the classical civilization / Christian paradigm, the two dominant theories, one from Aristotle and one from Ptolemy. Aristotle's theory of motion, again, his categories. He has natural motion as opposed to violent motion. And we'll go through all of this when we get to Aristotle. And then, of course, the geocentric system of Ptolemy, okay, with the different circles here. Here is the different circle. Here would be the different circle of Jupiter, and here is the epicycle of Jupiter, and Jupiter finally going around the epicycle as the entire epicycle goes around the different circle going around the Earth. And this whole mechanism we'll be able to describe, certainly, and question, does this explain, is a good question. And so let us end, let me show you a very pretty, I think I can get this. What happened? Okay. This is a wonderful animation from the observatory in Milan, in Italy. And once we can get rid of this nonsense. The first thing you're looking at here is an explanation, a theory by the man by the name of Eudoxus, the greatest mathematician of the ancient world after Archimedes. That's okay, everyone is comes after Archimedes. Very beautiful geometric model of Eudoxus, which explains the motion of the planets. This is, for example, the planet Mars. And you see it rocking back and forth. That's the famous retrograde motion. Although the moon and the sun move through the sky in one direction, we know that the motion of the planets is much more complicated. They actually at some point stop, go backwards for a while, and then continue on their journey going around the sky. In the ancient days, going around the Earth. And this is a very beautiful piece of geometry which explains that rocking motion going back and forth. Eudoxus was a contemporary of Plato, actually at one time a student of Plato, and Plato charged his students in the world to create a model of the sky. The phrase that's come down to us is to save the appearances, to create a mathematical model which will describe what we see in the sky every night. And this was the first attempt, this very beautiful, complex attempt by the great mathematician Eudoxus. What's the great weakness of this theory of these going around this sphere here? Notice that it doesn't really change its distance from the Earth. But we know planets do change their distance because they're sometimes bright and sometimes dim. And so this can't be the whole story. Okay? So now this is going to morph into Ptolemy's theory. Yes, here we have the deferent circle, we have the epicycle circle, and we have the planet. So here is Mars going around its epicycle, but what we see is this, right? We see the projection of the planet against the stars. This is what we see. We don't see this. There's no depth perception. All we see is the result is this. And you see the rocking back and forth, the same description that Eudoxus had. But now we do have the star brighter and dimmer and brighter and dimmer. Ptolemy has captured a mechanism to give us a changing brightness of the stars, as well as explaining the retrograde motion. And finally, the final warp into Copernicus, the most elegant of them all. The whole business of the rocking is nothing but a visual illusion. The planet does not rock at all. The planet goes around the sun in an orbit, very simple orbit, never changing its direction, but its projection, what we see, since we are also going around, you go back a little bit, go back a bit more. Since we see, come on. Since we see, again, we only see the projection against the sky as the Earth moves around. It gets a different perspective on the planet Mars. And the planet Mars seems to go backwards right there because the Earth is passing it by. a beautifully elegant solution of Copernicus, and the planet does not rock back and forth at all. It's as a simple a motion as the Earth's motion, all having a common motion going around the Earth, of course, in a perfect circle at constant speeds. In order to get the exact descriptions right, he's going to have to move to some epicycle as well, but I'm getting ahead of my story. Okay, see if we can get back to me. Hello. Okay. All right, guys. So that is where we are today. Any questions on anything that we've done today? Questions, comments?
I think it'd be interesting to know. I wonder, do you by any chance know when, at least in the West, when the term or infinite entered the languages of the Western world? Since so much of the early theories, you use the word finite a lot. When people started to use the word infinite, and when the idea even emerged.
It certainly emerged in Greek geometry. Certainly in Euclidean geometry, we have the notion of a line being extended indefinitely. I don't know when exactly the word was introduced into the language, but certainly the notion of infinity is very much prominent in Euclidean geometry. And there's a whole discussion about that, which, you know, but it's a very good question. Any other thoughts, comments before we go?
Peter, I was struck by the slide where you showed the view of the ancients as having a set of physical objects and the natures and so on that applied. No, I think it was even earlier than that, but similar. But it was saying that this applies to the terrestrial environment, which ends at the moon.
Yes.
And then from the moon on, it's an entirely different set of, it's constructed of entirely different matter and laws and so on and so forth.
Correct. That's correct.
And what struck me about that is it would seem natural to me for people to look up at the moon and say, boy, those look like mountains, as we see.
Oh, no, yes. Oh, no. Oh, but Mike, the mountains weren't seen until Galileo's time.
Okay.
They weren't seen until the telescope. This will become one of the great discoveries with the new technology that begins to tear down the old paradigm. So yes, you're absolutely right, but it doesn't come until the middle of the scientific revolution. Okay, so we'll call it a day. I don't like to keep you guys over too much. Look forward to my next email on Tuesday. And this presentation I'll be recording. I'll stop the recording right now. Will be out hopefully by this afternoon.